Hello, everyone. The title of his work is TAAF. TAAF actually stands for a Trace Abstraction and Analysis Framework. In short, it addresses challenges in trace analysis with combining different tools and techniques such as large language models, knowledge graphs, and stateful modeling. I presented this for my master's thesis a week ago, so this is basically the research I've done during my master's. I start by this question that what is kernel tracing? Everyone here is an expert in trace analysis, so I'll just go over it so quickly. We can think of kernel tracing as a very detailed diary that logs every kernel activity that is happening inside the operating system. It has several use cases. We can use it to diagnose some performance bottlenecks, for example, why a process is running slower than expected. We can use it for debugging complex errors that would be hard to replicate in simpler test cases. Using them, we can understand system behavior and verify the expected output and validate the correctness in our production. We can analyze the trace data after the fact, which we call postmortem, or while the system is running, which is just the live monitoring. Sorry. In this slide, I want to talk about the challenges with tracing and trace analysis. First of all, the most important challenge is the massive amount of data that gets generated. So when tracing applications like Chrome or MySQL, even a few seconds of data can generate millions of kernel events, each with multiple fields, multiple metadata, and analyzing this data is somehow challenging. Second is the multidimensional nature of trace data. By that, I mean every kernel event is not just a single data point. It can involve multiple entities like threads, CPUs, files, all interacting with each other. So we should handle and account for that multidimensional nature as well. The second challenge is the domain knowledge that is required for trace analysis. We have powerful tools like Intel V2 or Trace Compass. We can import traces, visualize some metrics, and gain some insights from actually the trace data. But the challenge with these tools is that they somehow limit flexibility. What I mean is that, for example, if I need to do a performance-based analysis or a security-based analysis or an IO-based analysis, I have to have those analysis modules already built in and already defined. And even with having those information, when I scroll through the trace data and find the relevant portion of the data that is necessary for my analysis, there is still some expert level knowledge required to understand and comprehend that data. So what we wanted to do in this research was to see how far we can push trace analysis using large language models along with other techniques like language graphs or stateful modeling. So our main research objective was to design a framework that help analysts, developers, and system admins to analyze trace data more efficiently, understand their systems more clearly, and answer basic or complex questions without being overwhelmed by the volume of data or the multidimensional nature. To achieve this objective, we structured our work into two tracks, the design track and the evaluation track. In the design track, we basically integrate large language models with knowledge graphs and stateful modeling to handle the multidimensional and temporal aspect of trace data so that they can work seamlessly. And in the evaluation track, we want to know what is the breadth and depth of the questions we can answer using this system, which I call TAAF. Here, you can see how we approached the problem of trace analysis using large language model. A very basic idea, if someone wanted to start with large language model and trace analysis, would be just to directly pass the trace data or kernel trace data directly to the large language model, ask a question, and look for the answer. But that basically fails because the amount of data is so huge and it easily surpass the context window of large language model. So what we do in this methodology is that we gradually transform the trace data into more structured and more meaningful representations, and then pass it to large language model for our analysis. We do this actually in 3 layers, all the way from trace data to state system, here from state system to knowledge graph, and from knowledge graph to the final answer. So the first layer, we import the trace data into the state system. So what is the state system? The state system is a time index database that keeps track of different system attributes. For example, a CPU that a thread is running on, or other different system attributes. It is already well established and used in tools like Trace Compass, and it actually does it using a tree-based structure, so we can look up these system attributes in a very efficient way, and that's why we are actually using this state system. So the next layer is going from a state system to knowledge graph. So when a user asks a system-related question, based on the user question, we only pull the relevant data, the relevant system attributes, from the state system. Then we have the numerical output here, but it still lacks some semantic. And we know large language models suffer from hallucination, they're confidently wrong. So what we did to reduce that is building a knowledge graph based on these attributes and based on these data, and then pass that knowledge graph along with the schema to large language model. So now it can answer system-related questions that is backed by trace data. So this is the general architecture and general methodology of our work. Now I want to go deeper into some of the components of TAAF. The first one is the state system. How it actually works is using 2 different trees, the attribute tree and the history tree. Attribute tree basically indexes every observable asset in the system. For example, CPUs, CPU number 2, current thread ID. So this is an observable asset in the system. Or threads, threads number 5130, the CPU that is running on. And we assign an integer ID to each of these observable assets, which we call it quark. Then we also have a history tree, which basically keeps the value for these quarks for every start and end time. So using these 2 trees, it can keep track of every system attribute over time. And it is efficient. We can look up the data in logarithmic time. And this is why actually we are using it in TAAF to handle the temporal aspect of trace data. The next component in TAAF is the knowledge graph that we are creating. We are using it to reduce the hallucination problem and also to make LLM reasoning more explicit so that it can refer to the nodes and edges that helped it to come up with the final answer. So our knowledge graph has several characteristics. It is directed and weighted. For example, a thread is running on a specific CPU, and for example, between 2 different timestamps, it happens 5 times, so we make the edges like weighted. It is query specific, which means that when a user asks a question about I/O, it yields a different graph than when it's actually asking about CPU thread activities. And it is also expandable, so we can add as much feature as we want to the nodes and edges, so it can help the future analysis. That was the first track, and for the second track, when we need to have a methodology to evaluate this framework and see how it actually works. So for our dataset, we use SciMark2 Java benchmark, which include 34 million kernel events. We need to do some configurations. We extract 3 different time windows from SciMark2 traces, 1 second of data, 10 seconds of data, and 100 seconds of data. We use 3 different large language models, GPT-4 1 Nano, which is a small model according to OpenAI documentation, GPT-4o and GPT-04 mini, which is a reasoning model. So having 3 models, 3 time windows, we have like 9 traces slices. We also need a baseline. As I said, a very nice baseline would be just to pass kernel events, but because this usually fails, for the baseline, when the user asks a question, I pull the information from the state system, directly pass it to large language model for the baseline, and add this knowledge graph builder component and create the knowledge graph as the TAAF setting. So we have 2 different input variants in the following research questions that I want to talk about. Finally, we also need a benchmark to actually evaluate TAAF. We need a set of questions with reference answers. Here, there is some kind of a gap in the literature. We have benchmark for LLM evaluation, but they are in other fields like codes, mathematics, physics, and so on. So what we did here was to create a benchmark. We created TraceQA 100 over SciMark 2 traces, which includes like 100 questions in different format, multiple choice, true or false, or explanation questions. And it covers different reasoning, like single hop reasoning or multi-hop reasoning. So we have 100 question, 9 pair of large language model and time windows, and 2 different input variants. So overall, it gives us 1,800 Q&A items. And one thing is that if you ask large language model a same question, it gives you different answers each time. So to account for that stochastic nature, we ask each question 3 times. So overall, we'll have like 5,400 data points. In this table, you can see how the actual questions would look like in TraceQA 100. For example, one question would be, what is the total accumulated CPU time for thread 51 to 30 on CPU 0? So this is a single hop question because it's only targeting one edge between 2 nodes in the graph. And we are asking this question from 1 second of data from the middle of the data. And here we have the reference answer for that. Or another question would be true or false. The busiest CPU also runs the most number of unique threads. So this is a multi-hop question because it requires reasoning across multiple entities and multiple relationships in the system. We also need some kind of rubric for labeling the responses. Here we use a 3-point labeling system. It gives 0 to those answers that are fully incorrect, and it gives 1 to answers that are correct and actually matches the ground truths that we extracted. We also wanted to give some partial credit to those answers that, for example, they extract the relevant entities and relationships, they reason correctly, but there are some minor issues, some fractional issues. So we have like a more detailed rubric for the annotators when they are labeling, but this is the system we are using for labeling responses. And the main metric we are using is the accuracy, which is just the weighted average of the labeled responses. And for one research question, we also use consistency, which basically measures how peaked or spread out the model is. For example, a very consistent model always gives 1 or always gives 0. It is, again, consistent, but consistently incorrect. Here you can see the set of research questions. We categorize it into 2 phases. The first phase basically wants to see how this framework, how TAAF actually perform across different question types, different time windows, different large language models. And the second phase wants to focus on some specific parameters in our system. For example, the temperature parameter of large language models and its actually impact on our system. I'll go over each of these research questions. Here is the first research question. How does TAAF's accuracy vary across different user query types and different graph question types? So we had 3 LLMs, 3 time windows, or we will have 9 tables. I will show one of the tables here. This is for GPT-4 1 nano, 1 second of data. Here we have different query types, for example, true or false, single hop or multi-hop. Here we have our baseline, which is just the output of a state system directly going through LLM. And here is when we actually create a knowledge graph and pass that knowledge graph to large language model. So for example, for true or false single hop questions, we have 75% accuracy in the baseline setting, and we have like 88% accuracy when adding knowledge graph. To explain the numbers in these 9 tables, I made some visualization. Maybe you can see it better here. On the left side, we have the baseline, and on the right side, we have the full TAAF setting with the knowledge graph. Here we have different question and graph question type, like multi-hop, single hop, or true or false, explanation, multiple choice. You can see that almost in every combination of questions, we have improvement when adding knowledge graph. There are some insights we can get from this chart. For example, the minimum accuracy for multi-hop explanation questions, both in TAAF and both in baseline and in the TAAF settings. We have the maximum accuracy for single hop true or false question, which reaches to almost 91%. And one other insight is that multi-hop questions have actually the most improvement. So for multi-hop true or false question, the accuracy improves almost 30%, which is interesting. The second research question is that what is the effect of time window on the accuracy of the responses? Here we have like the time window, 1 second, 10 seconds, and 100 seconds of data, and we have different large language models with different colors. As you can see, when we increase the time window, the accuracy starts to drop slightly. And what I need to mention is that these solid lines are the TAAF setting, and these dashed ones are the baseline setting. One thing that we can notice is that the rate of decline is steeper in the baseline in comparison with the full TAAF setting. I think this is because when we increase the time window, when we have the knowledge graph, we might need to add some nodes and features, but what we have to do mostly is to update node features or edge features. So the amount of data does not increase as much as the time we are just directly passing output of a state system to the large language model. So basically here we have more data to process, so the rate of decline would be steeper. The third research question asks, to what extent does adding knowledge graph improve accuracy? We have average improvement of 21.5% for every model and time window combinations. The maximum accuracy, maximum improvement is for 100 seconds of data, O4 mini model, which is a reasoning model. And the minimum improvement is for 1 nano, 100 seconds of data. One thing that we can see in this chart is that when we increase the time window, we also see that our system better utilizes knowledge graphs and gains more accuracy when we have like longer windows. Next is how does performance vary across different large language models? We can use the same chart, and we can see that this green one is the reasoning model O4 mini. It has like the best performance overall. Then we have GPT-4o, which is shown in orange, and GPT-4 nano in blue. These 4 research questions basically measured how TAAF performs across different questions and different settings. From now on, we have 3 research questions that focus on specific factors in TAAF. And one thing that we had in our architecture was that when we wanted to pass the knowledge graph to large language model, we also passed the graph schema to it, which basically explains node types and features. We wanted to know where LLM is actually using it or not. So what we did was to do an experiment on 1 second of data with GPT-4 once with this schema and once without this schema, and we saw an 8% improvement. So we saw that it's actually using it, so we keep that. In our approach. The next question is that how does the temporal location affect the accuracy? It means that if I get the 1 second of data from the start of a trace or from middle of the trace or from end of the trace, whether it differs or not. And we see that it actually remains robust, and we only have 3-4% difference. So we can actually rely on that, and we don't need to fine tune based on the temporal location. The last research question is that how does the temperature parameter of large language models affect this TAAF accuracy? So temperature is a number between 0 and 1. The closer to 0 we are, the more deterministic the model is, and as we increase it, the model will be more random. So we did our experiment on 10 seconds of data with GPT-4 with 5 different temperatures. And we saw that we have the best accuracy and consistency when we ask the model to be more deterministic in comparison when it is actually more random. So in conclusion, in this study, we introduced TAAF that could convert low-level kernel events into human-readable insights and make trace analysis a little bit more accessible. We also released TraceQ800 benchmark, and we got some insights that, for example, graph grounding can improve the accuracy by average 21%. There are some limitations and trace the validity of this study. For example, one is that when we are using humans for evaluating the responses, there is always the risk of bias. So here we also have this risk as well. We only actually tried SciMark2 traces. It is better to test other traces and even not kernel traces, user space traces, and see how that performs across other traces. And for future directions, there are different directions, but personally, I think the most important one is to apply this idea to production scale systems and see whether we can actually find a bug or actually find a starting point for debugging the system or not. But there are other future directions like embedding it with AI agents or compare it with other approach like creating temporal knowledge graphs and so on. And yeah, that's it. Any questions?
So maybe a segue to the talk just before yours. Do you see a way we could use LLMs to do analysis and comparison of various schedulers? To kind of ask it what is causing the behavior, what could be tuned into within each scheduler to improve performance, make better scheduling decisions. So I see that the model you're looking at is really what's running on each CPU. So you're not that far at the model level from actually having information about the run queues, the migration of the task, and so on and so forth.
Exactly.
That would allow you to reason on what the scheduler is doing.
The problem is that we have hallucination when we are using large language models. So what basically this research was focusing on is how to reduce that. And for that, we used knowledge graph. I don't know whether we can create graph for schedulers and does it have entities or no. But we should find a way to somehow structure the information in a meaningful way so that LLM can better reason and just does not make incorrect facts. But I think it's going to be challenging to use that for schedulers.
So what? So do you have examples of what you put in the knowledge graph? What does it look like?
Yes, actually, let me bring this slide.
Yeah, I would love to see a physical or an actual question and answer.
Yeah, I really love to show a demo here, but it wasn't possible.
That's fine, but can you?
Yeah,
We can imagine if you narrate it.
yeah, but just let me bring the knowledge graph. Okay, here is the knowledge graph that is created.
Can you
Based.
describe it because it's too small for us to read?
Yeah, yeah. Assume that a user is asking, for example, what CPU is handling like more number of threads between different two timestamps. So based on based on the user's question, we pull the relevant information from the state system for that specific CPU or CPUs. And then we will have like some attribute, for example, the execution time, the thread that it was running on. So based on the output of a state system, we create a graph. Here we have like 4 CPUs based on the user question here, CPU 0, CPU 1, CPU 2, and CPU 3. And we have the threads that are working with those CPUs in that specific time interval. So this is how the actual graph would look like. And we have like features, for example, for an edge from thread to CPU that during this time window, how many times it run on that CPU, how long it run on that CPU, and like other metrics, we can add it as much as we want. Or for example, for a CPU thread, we can have edges like the busy time, the number of threads it handled, total accumulated time. So we have different features. So this is going to be a graph generated based on a specific question that a user asked. And then we pass this graph to large language model for reasoning and answering. So we also ask large language model to specifically refer to nodes and edges that helped it to come up with the answer.
If I understand correctly, so you start with a user question.
Yeah.
You have the state system from Trace Compass.
Yeah.
Based on the question, you scan the content of the state system for the relevant time frame, and from that you generate the knowledge graph, which is fed to the LLM.
Exactly.
Have you considered taking also the segment store so that you can get like your distribution, frequency domain analyses, basically some more aggregate data that would be harder to trip up and hallucinate on?
Mm-hmm. Actually, I did not, but because we can make this knowledge graph based on the user query, we can add any aggregated metric you mentioned as the features in nodes or edges, so we can integrate that domain knowledge that I mentioned in the graph.
So with TAAF, I ask, why am I so slow? And it will generate an answer. That's the end goal, right?
That's an ideal goal, but currently when you ask such a question from the whole system, so it needs to relevant all the data. So
of course, I'm just trying to...
Yeah, but ideally yes. Ideally yes, but yeah, for now we should ask like more specific questions.
Of course. What kind of question would we ask?
For example, we know that in 2 timestamps, for example, in 1 second of data, in the middle of the data we see there are some anomalies, and we are suspicious that there is a problem there. So we ask, for example, what CPU is like very busy at that current timestamp, what threads are working with that CPU, what are the files that are interacted, and this is the question, actually.
Okay.
Yeah, the question is, how do you select the part of the knowledge graph who is relevant to the question?
Sorry, I missed it. Can you repeat?
So how do you know which part of the knowledge graph to create when the user asks a question?
Mm-hmm. Basically, we have to, the first step is to querying the state system based on the user question.
Yes,
so the question is, how do we know what to query in a state system? So here we again rely on large language model. First of all, here we have a query plan I didn't mention. Based on the user query, we extract the, for example, source and target that might be included, the CPUs or threads or files or anything that might be the source of the analysis and might help us in getting the final answer. So we extract that, and we extract the timestamp that might be relevant. So when a user asks a general question like why the system is slow, so generally it would be the whole system. But if it asks like more detailed one, we can narrow down the timestamp. So we use large language models again for like having a starting point for what to actually query from the space system.
And maybe the question is why this one is not enough? Why this step is not enough to ask a query language where you can do some whatever, for example, let's get with SQL or whatever, when the LLM as the first step can just create new query to the knowledge and directly give you.
Yeah, this is a good question. So I think here we need to have like more work on how to query actually a state system or other things to specifically extract the wanted attributes. Any more questions? Okay.
In the limitation and practical validity, you mentioned the benchmark limits rare complex scenarios.
Mm-hmm.
What do you mean by complex scenario?
Yeah.
And I'm thinking about your presentation yesterday where
Mm-hmm. So, as I mentioned, there is a lack of benchmarks for trace context and evaluating large language models in the trace context. So we created ours, which only includes 100 questions. I believe 100 questions are absolutely not enough for covering different scenarios in the system. Maybe we miss some of the very specific scenarios that result in bugs. So this is the limitation I mentioned there, and we need like maybe extending our data set, or even we need like more benchmarks from the industry to be able to better validate this system. Thank you.
Thanks.